The last time I've been in Vilnius was 38 years ago. I was a school child on a school trip. So I don't remember anything. Anyway, so I realized I won't have time to tell you everything about optical neural networks, but I want to start with what I told you about last time, and then report on the progress achieved in the past year. So last year I've been talking a lot about overcoming diffraction limit in microscope resolution, and to remind you, the microscope resolution is limited by the diffraction on the objective lens, right? So if you try to image a point source, then you'll get some kind of blur at the output, which is called the point spread function. And then if you have two sources that are close to each other, then the point spread functions will coalesce, and eventually you won't be able to resolve them. So you won't be able to tell what the distance between them is, or even tell that there are two sources rather than one. And in the past century, a number of ideas have emerged on how to overcome the diffraction limit, which can be divided into like 2 or 3 large families. One family involves near field probing, right? You have some kind of probe scanning directly at the surface of your object. And because there is no objective lens, there is no diffraction. The second family is you invoke some kind of nonlinear effects in your system, which make individual fluorescent emitters in the object to light up one by one. And then you get a sparse emitter rather than a dense emitter, and it's much easier to localize each individual emitter. You get super resolution. It's like Sted's, Baum, Storm, and so on, the Nobel Prize 2014 in chemistry. And finally, there are quantum methods that use squeezing or Fock states or entanglement to reduce the effective wavelength of light. Now, all these methods are nice, but they have a common shortcoming that they require some kind of active interaction with the sample, right? And this is quite a significant restriction because even in microscopy, there are samples that are fragile, that do not allow near field probing or do not have the required nonlinear optical properties. But outside microscopy, these methods are completely non-applicable because, for example, in astronomy, how would you do near field probing of a star? Similarly for remote sensing, satellite imaging, surveillance, and so on. So it would be much nicer if we could develop some kind of passive microscope, a passive imaging device that would just by passively analyzing the light in a different way, enhance the resolution rather than actively interacting with the object. And if we develop such a device, it would change the face of basically every field of science and technology that has to do with optical imaging. But of course, it's a tall order because, Abbe and Raleigh were intelligent people. Their science was based on solid grounds. So can we beat the diffraction limit? And the answer came with Man-Kei Tsang, who about 10 years considered imaging as a quantum sensing problem. So he thought, we need to evaluate certain parameters of our image, certain properties. What is the optimal measurement that give you the best evaluation of the parameter of interest? And then he said that this optimal measurement might not necessarily be imaging. So imaging meaning evaluating the intensity, measuring the intensity of light, the transverse distribution of the intensity in the image plane. Instead, you may want to use a different basis. So you may want to decompose your image field into a basis of some kind of transverse modes. Typically, in his case, it's Hermite-Gaussian modes. And then you measure the intensity in each mode, and use the measurement with the result to reconstruct the parameters of interest, and you can then reconstruct these parameters with much higher precision. And the specific problem that he considered is measuring the separation between 2 point sources. And here's a slide that shows the intuition how it works. Suppose I image a star, and in my image plane, I put a filter that only transmits Hermite-Gaussian 0-1 mode. Right? Now, Hermite-Gaussian 0-1 mode is completely asymmetric, meaning that if the star is on the optical axis of your apparatus, no light will be transmitted. But if the star is displaced, the image is not completely symmetric. There is an anti-symmetric component. Some light will be transmitted, and even if there are two stars, still, even because they are asymmetric, their intensities add, and again, you have light transmitted, even if the stars are within the diffraction limit with each other. And one can show mathematically for quantum Fisher information, I'll show you in a moment, that this measurement will be much more precise than via direct imaging. The intuition behind it is quite simple. Well, basically, you have to distinguish here between no light and the little light. And this distinction can be made with much more precision than in regular imaging, where we're trying to distinguish between a picture and a slightly different picture, right? A picture of a single point source or two coalesced sources. Now, this plot here shows the Fisher information, so that's like the quantum part of it, shows the Fisher information as a function of emitter separation, again, for the task of estimating the distance between 2 point sources. If the emitters are widely separated, then direct imaging gives you the same Fisher information as the quantum limit, right, given by this green curve. But then as you reduce the emitter separation, direct imaging gives you less and less information for the reasons I just explained, but this Hermite-Gaussian mode detection gives you constant Fisher information, which coincides with the quantum limit. So here at small emitter separations, we'll have an infinite advantage of quantum compared to classical. Well, sorry, not quantum compared to classical, of this Hermite-Gaussian imaging compared to direct imaging in terms of the quantum Fisher information. Now, our contribution to the field has been to extend this technique to full imaging. And the idea is quite simple. Instead of just measuring in a single mode, Hermite-Gaussian mode 0, 1, we measure in multiple Hermite-Gaussian mnth modes. And then a simple calculation shows that the amplitude associated with the mnth mode corresponds to the mnth moment of the source field distribution. So if you measure in a bunch of modes, you have a bunch of moments of your distribution. As we know from statistics, from this you can estimate the distribution itself. And we call this method Hermite-Gaussian microscopy or Hermite-Gaussian imaging. Now, in theory, you have to use, as I said, you need to sort into Hermite-Gaussian modes, which is challenging. I mean, people do it, like there is even a company at Kai Labs that some of you are familiar with that sells such devices, about 70,000 euros a piece. But it is, it's quite difficult. I'll show you in a moment. It doesn't give you enough fidelity. So what we do instead is we use heterodyning. That is, we use the property of the heterodyne detector to only detect light in the mode corresponding to the mode of the local oscillator. So you see, it's difficult to sort modes, but it's quite easy to prepare light in a Hermite-Gaussian mode, in a given mode. You can just use an SLM. And then you use a heterodyne detector and measure the amplitude for each mode one by one. And with this, we obtained a bunch of results. I showed them to you last time, so I won't repeat. But here's kind of what our pictures look like. We take an image. It's a toy microscope. It's not yet a proper microscope. It's a toy microscope where you have a sub-millimeter image displayed on a DMD. And you kind of artificially impose diffraction limit by applying a narrow aperture. And then direct imaging will give you this blurry picture like this, and our Hermite-Gaussian method will give you a picture like this. And we've tried it in a bunch of different settings, such as with coherent light corresponding to this picture, with incoherent light, and we combined it with another resolution enhancement method called confocal illumination, and we observed cumulative resolution enhancement, right? So we get a factor of 2 to 4 resolution enhancement. And to show you like the first new result, we've done it now with a proper microscope. So kind of a similar setting, coherent light, heterodyne detection. And here's what it looks like with just an edge of a reflecting surface. The regular wide field imaging gives you like this, a resolution of about 600 nanometers. When the confocal setting, so when you focus your illumination, you improve your resolution to 300 to 400 nanometers. But then if you apply also Hermite-Gaussian imaging, you get a much sharper edge. So significant enhancement. And then we tried it with a fluorescent target. And again, you get resolution enhancement. It's not as obvious, but you can see the size of number, like if you look at the width of number 1 here, it's significantly narrower than the width of number 1 here. And we also tried it with a biological tissue, namely a supermarket pork. And again, we get resolution enhancement. Now, the next slide I was kind of hesitant to show you because this is, so I should say that all of this was discovered by my postdoc Lee. I still don't understand how he arrived at this idea, but unfortunately I cannot tell you what basis we use. It's not a Hermann-Gaussian basis, but we are trying to patent it, and we're trying to, commercialize this. So that, it's not in my style to hide information, but in this case, people's careers depend on it. So I'm sorry. But anyway, we use a secret basis. And we use, in this case, we don't use homodining, we actually use proper mode sorting. And our object is the same fluorescent target. Now, these numbers, what do these numbers mean? The numbers are the number of lines per millimeter. So here you can see 4,000 lines per millimeter, and you can see that they're fully resolved, right? So it means that the distance between the lines is 250 nanometers, and this little gap that you can see fully resolved here is 125 nanometers. And you can, with this method, you can fully resolve it. So it's, well, you see a blot here, but I think the blot is just a defect of the target. But I think it's pretty amazing that you can resolve, that you can have this resolution. And there's an added bonus. You have, this method is insensitive to longitudinal detuning. So if we detune our microscope out of focus, as we've all experienced, the direct image fails. It starts looking like this, but our method still works. With some reduced resolution, but still works. Now, okay, how is it all related to optical neural networks? The answer is that this mode sorter is essentially an optical neural network. So what Kai Labs will sell you, and this mode sorter, is an optical neural network. So there'll be some kind of hologram here prepared, and the light will bounce off this hologram several times, right, of this faceplate, and then we'll give you sorted modes, so different spatial modes will go into different direction. Now, so far, this was kind of, this faceplate was kind of pre-calculated to do, for example, Hermann-Gaussian mode sorting. And the question that we ask, can we actually train this optical neural network using methods of machine learning? Can we train this optical neural network to achieve a highest possible resolution, or more generally, to optimally extract the parameters we're interested in our object? So now it's a machine learning problem, and if we limit the number of photons, it's a quantum machine learning problem. So here's an example of more precisely what I mean by this. You've seen this plot before. This is the problem of measuring separation between point sources as a function of that separation. Fisher information is plotted. Again, dotted line here is direct imaging, goes to 0 at small separation. The top line is the quantum Fisher information, ultimate limit. Now, if we have an ideal Hermann-Gaussian mode sorter, but that can sort only 9 modes, right? So some degree of realisticity, then we have a curve like this. So for small separations, it achieves the ultimate limit, but then for larger separations, the object no longer fits within the, within small low-order Gaussian modes, so you get reduction. But that's not possible to make. What's possible to make is this mode sorter, so again, a faceplate. So suppose you have a 3-layer faceplate trained to optimally distinguish Hermann-Gaussian modes. Well, in this case, you get this orange curve, which only barely improves on direct imaging. You see, doesn't really give you significant advantage. So if you try to make a realistic apparatus to distinguish Hermann-Gaussian mode, the performance is not perfect. But if instead you train your faceplate specifically to optimize the Fisher information, then suddenly your performance is significantly better. Sorry, the green curve here shows significantly better performance. It still falls to 0 at 0 separations, but it's much better than direct imaging or this naive way of training. So, okay. So to formulate this more generally, think of computer vision, right? Computer vision, of course, is very common. It's like, 20% of the entire machine intelligence market. And the way computer vision is done today is that you take some kind of image of your object with a digital camera, and then you analyze this image with a digital neural network to extract the parameter that you're interested in. Now, many machine learning problems involve settings with photon-starved settings, right? For example, a self-driving car, it's trying to distinguish a pedestrian in a night street, or read the message of a road sign, or a microscope is trying to distinguish bacterium from a virus in phototoxicity condition, or we're trying to find an exoplanet, right? We have a limited number of photons, short noise insignificant. In this case, we have to use these photons wisely. In this case, it's not necessarily a good idea to image them, right? Because we're not interested in the image. We're interested in some parameters of your object, such as, whether it's a binary star or what the message of the road sign is, right? So direct image reconstruction is not optimal. Instead, what you'd want to do is first pre-process your light, again, generally speaking, with some kind of optical neural network, then detect it, and then post-process it with a digital neural network, right? And you train these two neural networks in concert, and the good news is that, well, if you have a limited number of photons, you have these quantum criteria that determine your ultimate performance, right? Which is quantum Fisher information for regression and Hellstrom bound for classification, right? So you can check once you trained your system, you can tell how good it is, how far it is from the ultimate limit. And here's an example, an experimental result. Here, we apply an optical neural network to distinguish these fashion amnest images. So 10 categories of images like t-shirts, bags, pants, and so on, right? And we build an optical neural network, and we say, suppose this emits just one photon. How precisely can we distinguish? Well, just two classes. Let's say we want to distinguish a t-shirt from a pair of pants. This table tells you this. So it's not a regular confusion matrix that you see in machine learning often. This tells you the accuracy for pairwise imaging, pairwise distinction, right? So, for example, if you like this 0, 1 means you're trying to distinguish a t-shirt from a pair of pants. The ultimate, the quantum limit is determined by the Hellstrom bound, which is about 77%. With direct imaging, if you just have one photon and you direct image it, then the possibility to distinguishing it is only 58%. Now, okay, 58 sounds like a lot, but actually 50% means complete confusion, means you cannot distinguish at all. You have 1/2 probability. And with experiment, we achieve 72%, so significantly closer to Hellstrom bound and significantly surpassing direct imaging. So, yeah, so that's the first step towards the single photon image discrimination. Now, I want to proceed to the next part of my talk, which is, what happened? Sorry. To the next part of my talk, which is combinatorial optimization, so something that we've done recently. You might have heard about, combinatorial optimization in general is the problem of finding an optimal solution in some kind of discrete set. The most common one is a so-called Ising problem, where you're given a matrix, Jij, and you're trying to find a vector which minimizes this objective function h, which looks like Ising Hamiltonian, but again, it's not the it's not the solid state physics problem. It's an abstract mathematical problem that resembles the solid state Ising model, right? So Jij is not necessarily interaction of nearest neighbors. It's some kind of matrix which can be fully connected. And yes, so this Ising problem is ubiquitous in science and technology. It's present everywhere. And then not surprisingly, there is a whole industry of methods trying to solve it. So there are software techniques, digital software techniques, digital hardware techniques. There are quantum techniques. For example, the D-wave computer is, well, basically the entire purpose of the D-wave computer is to solve the Ising problem. And then a new player in this field appeared some 10 years ago, the so-called coherent Ising machine. What's a coherent Ising machine? It's as follows. You use, here is a sequence of pulses of optical parametric oscillators, right? So, forget this displacement for now. You have a pulse of light circulating in a fiber loop, and here's a squeezer. So you have an optical parametric amplifier plus a cavity, an optical parametric oscillator. You know that optical parametric oscillators are bistable. That is, they can take phases of either 0 or pi randomly. And if there is no coupling, these phases will be completely random from pulse to pulse. But what they do is they implement coupling of these oscillators. That is, they do a measurement. They split off a little part of the squeezer's output, measure the quadrature, memorize it, and then using a digital computer, calculate this quantity, right? This matrix vector product, J times X, and then apply it as a classical displacement to each incoming pulse. And then you get coupling, and this coupled system will no longer be random. The phases of this coupled system will then no longer be random. It will then magically represent a solution to the Ising problem. So so they've shown quite a lot of advantage here. They've compared it with classical, with digital algorithms, and they even compared it with D-Wave, showing like significant advantage compared to D-Wave. And a further advantage is they can have full connectivity between the nodes, and now they've gone up to 100,000 nodes. Now, this was quite impressive, but of course, this scheme is entirely classical. You see, you don't have any kind of quantum interaction between the pulses. Instead, you have, classical measure and feedback technique, which prevents entanglement and therefore, prevents any kind of quantum advantage. And moreover, essentially, it's a digital computer because the most computationally expensive operation in this machine is this matrix vector multiplication, and it's performed entirely digitally. And then the question arises whether it can be simulated by a classical computer, which we answered in this paper, but I won't have time to talk about it. But instead, basically, to give you a general picture, right? So the D-Wave annealer, when the D-Wave annealer appeared, their sort of claim to fame was that they surpassed classical simulated annealers. And then optoelectronic coherent Ising machines surpassed the D-Wave annealer. And then, classical simulators, then we and other groups developed, surpassed these optoelectronic coherent Ising machines. Now, what we really want to do, how can we fix the situation? The answer is, can we still make a coherent Ising machine, but make the coupling not digital, not electronic, but all optical? And here's the idea. Again, you have the system of coupled optical parametric oscillators, but now these OPOs are spatial rather than pulsed, and then you couple them via a matrix vector multiplication technique, again in space, right? So a circuit that looks like this, right? And now in this circuit, you have, you can have entanglement, right? Because all the interaction is optical. And moreover, even if you don't have entanglement, you still have advantage due to optical computation rather than digital computation. Now, if you look at the circuit, this is essentially, again, an optical neural network, a recurrent optical neural network, because you have a linear layer here, nonlinear activation here, and then the only thing that's different is that you take the output of a layer and send it back to the input of a layer. So essentially, it's a recurrent optical neural network, right, which comes to a steady state, which happens to represent the solution to the Ising problem. Now, how do we want to implement this in practice? We use this phenomenon of polarization self-rotation. Well, the phenomenon is that if you take elliptically polarized light, send it through nonlinear medium, such as well, a vapor cell, then the polarization ellipse will rotate. Now, the physics of it is quite simple. You can think of this ellipse of consisting of two circular components. One component is stronger than the other. That's why it's elliptical. They interact differently with because they have different strengths. They interact differently with the atomic system. They experience different refractive index. As a result, they'll have a phase shift, which manifests itself in the rotation of this polarization ellipse proportional to the ellipticity. We've used back 20 years ago, we used it to implement squeezing. So basically we pump it with horizontally polarized light. So in this case, it's, thank you. In this case, it's linear, so there is no ellipticity. However, there is always some fluctuation in the other polarization component, in the horizontal component. There is always some kind of, well, some microscopic amount of light present, a quantum fluctuation. Meaning there is always some microscopic ellipticity present, resulting in microscopic self-rotation, resulting in a transformation of the vertical component phase space like this, a shear of the phase space resulting in squeezing. So that was 20 years ago, and now we started thinking how to apply this to make an Ising machine. And the answer that we came up with is as follows. Well, why don't we take the vertical, so this was an OPA, let's make an OPO, right? Let's put this vertical polarization in a cavity, and then look what will happen. Look what will happen. Initially, you have, again, some microscopic ellipticity, right? Self-rotation gives you a shear, but then when it travels through the cavity, you get the phase shift, so you come here. Again, once you enter the cell, you're posed to experience self-rotation, but with a higher amplitude, so you get cumulative effect. And moreover, dependent on the sign of this initial quantum fluctuation, your final state will be like this or like this. So you will produce bistably, randomly, one of the two elliptical polarization pattern. We observed this experimentally. So here, basically, is an oscilloscope trace which shows, well, one of the two helicities, and you can see it's completely random. We've shown by statistical methods that it is indeed random. And, well, here's the last slide. This shows what we want to do in the experiment next. We want to actually make it an Ising machine that is pump. So far it's a single OPO, but if we pump our rubidium vapor with multiple spatially separated pulses, it will be multiple OPOs, which we can then couple using this SLM, and this will give us an Ising machine. Thank you for listening.
So thank you very much. Are there questions? Yes.
Very interesting talk. Thank you. Coming back to the first part, where the task is to distinguish these 2 point sources. You're always plotting the Fisher information per photon there, and it remains high even for zero separation. But if I understand right, at that point you would have no signal in the higher moments, right? So what would you get if you compare a situation where you, for example, illuminate for a fixed time with a fixed intensity in both cases and take into account that the signal levels may be different?
Zdenek, do you want to answer this? No, I think it's per emitted photon. So it's so even though you get the fact that you get no photons is an indication that your separation is zero.
So even for zero separation, you get information.
That's right.
So maybe it's Danny.
Okay, Alex, thanks also for nice talk. But actually, I would like to comment. You talk about advantages of this, let's say, quantum inspired processing, but there are, of course, disadvantages with respect to this direct imaging, namely that you must assume from the very beginning what do you want to observe, because it's model dependent and you can evaluate the Fisher information. And concerning this talk, actually, the point in this zero are a little bit tricky because, frankly speaking, all these methods are strongly biased. So it means that you are not allowed to use this grammar in this form. And especially here, if you are even thinking in terms of classical image processing and you see that there is just single point and you know there are just 2 points should be there, you will clearly say there is a zero separation. So frankly speaking, we are of course although using this kind of simplified argumentation, but I guess you agree with me that it's a little bit, let's say, somehow, let's say, this is not completely fair to say that the zero Fisher information is zero and the classical image processing fails. Yeah, so because there is the very different regime. Right?
Absolutely, yes. So it's indeed biased, right? Because the reason is that formally this argument, still is valid, but the problem arises elsewhere. Is that the Fisher information is not a perfect, is not the proper method to evaluate precision because it's a bias because unbiased estimators are not optimal. The reason being that the point separation must always be positive. And we must take this, and this means that the biased estimator taking this restriction into account is better. However, in spite of this, we still believe that there is advantage. Well, basically, I've shown you experimentally that there is advantage. Some of the experiments are done with classical noise, but if you do a careful quantum analysis, you still get significant advantage in resolution.
There's one other quick question. Yeah.
Well, that's right. So you can combine it with confocal illumination, right? And you have scanning, and this method that I showed you, it works with large objects as well. So that takes this issue into account. Sorry. Well, here the object is infinite, right? It's a large fluorescent target. Here in this experiment, we use Hermite-Gaussian basis and we scanned in the confocal regime.
Okay, so I think we have to go on right now because the time advances. But let's thank the speaker again.
Thank you.